this videotape, we're going to review our work on graphing. In earlier videotapes, we learned how to graph straight lines, parabolas, circles, ellipses, hyperbolas. And while you may have understood each lesson while I was explaining it to you, sometimes when they're all finished, you get a little confused, and it's a little hard to distinguish between the different equations. The purpose of this tape is to help you to differentiate between different algebraic equations when you see an equation to know what kind of a curve it is. And this, of course, would help you in sketching it. Let's start with the following. 4x plus y equals 16. Okay, now 4x plus y equals 16. Some of you may say right away, well, that, of course, is a straight line. And it is. It comes under the general form ax plus by equals c, where a, b, and c are constants, and a and b are not both 0. Notice that this equation is first degree in x and y. There are no squares. Okay? X and y appear to the first power only. And, of course, this is a straight line. Once you know it's a straight line, then, of course, graphing it is very simple, because a straight line would be determined by 2 points. All you need to do is to find 2 points on the straight line. You connect them, and you'll have your graph. Okay, and what 2 points? Well, intercepts are usually very simple points to get. We can say when x is equal to 0 here, we will find the y-intercept. When x is equal to 0, y is equal to 16. Similarly, when y is equal to 0, 4x is equal to 16, x is equal to 4. And while 2 points do determine a straight line, sometimes people like to plot a third point just to be sure that their line is correct. Okay, so let's just pick another value for x. For example, x is equal to 1, in which case we'd have 4 plus y equals 16. Y would be equal to 12. Okay, let us now plot these points. Here we have 0, 16. 1, 2, 3, 4. 4, 0. Connect these two using a straight line. And then just check to see if the third point is on the line. 1, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it comes awfully close. I'm not doing too accurate a job here, but this sort of convinces you that the other points are correct. Of course, if your third point is not on the straight line, it does not mean that the third point is wrong. Perhaps one of your other 2 points is wrong. But anyway, the third point does provide a check for you. Okay? An equation of the form ax plus by equals c. Its graph is a straight line. Okay, now what about just changing this a little bit? Let's change it to 4x squared plus y equals 16. I have changed this so that now this equation has an x squared in it. Instead of x and y both appearing to the first power, only we have x appearing to the second power, y appearing to the first power. This is the equation of a parabola. Okay, if you have a curve of the form, let's say ax squared plus by equals c. This would be a parabola. This would be a parabola whose vertex is on a coordinate axis. In this case, a parabola whose vertex is on the y-axis. The more general equation of the parabola would also have, say, a term involving x. For example, ax squared plus by, maybe plus dx equals c. Okay, but this is certainly a parabola. Whereas all we did was change 4x plus y equals 16 to 4x squared plus y equals 16, and we now have an equation of a parabola. This one was a straight line, and this is a parabola. Okay, if you'd like, you could write this as y equals 16 minus 4x squared. But, of course, it can be written in any form whatsoever. Okay, let's try to sketch the graph here. Once again, intercepts are very useful points to have. When x is equal to 0, y is equal to 16. When y is equal to 0, we get that 16 minus 4x squared equals 0. 4x squared equals 16. x squared equals 4, x is plus minus 2. Okay, so we have plus and minus 2, 0. And it turns out the vertex is also at 0, 16. And let's plot the points that we have. 0, 16. 2, 0, and minus 2, 0. It's a parabola. Okay, vertex at 0, 16, opening down like that. Now, if you are not aware that it's a parabola, then you might say just plot a few points. For example, x equals 0, x equals 1, get 2 points, say, on the right side of the turning point, and sort of connect them and think it looks like a straight line. So it's helpful to know, just from the equation, what kind of curve you're talking about. Okay, what if I had, going back to the straight line that we had, instead of making it 4x squared plus y equals 16, what if I'd made it 4x plus y squared equals 16? This would also be a parabola. Here we have something like ax plus by squared equals a constant. The important thing is that x or y appears to the second power. In this case, y appears to the second power. X appears only to the first power. That's how we can tell a parabola from a straight line. In a straight line, x and y both appear to the first power only. Okay? In a parabola, one, but not both of the variables appears to the second power. The other only appears to the first power. So when neither x nor y is squared, we have a straight line here. Here, x is squared, but not y. Here, y is squared, but not x. This is also a parabola. Okay, and once again, intercepts are going to tell us what's going on here. Here, when x is equal to 0, y squared equals 16, so y is equal to plus or minus 4. And when y is equal to 0, 4x is equal to 16, x is equal to 4. So we have 4, 0, 0, 4, and 0, minus 4. It can also be shown that the vertex here is at 4, 0, and the parabola looks something like this. Okay, by the way, the forms that I have given you for parabolas, these are parabolas that have their turning points or their vertices on the coordinate axis. Okay, in this case, it has the vertex on the y-axis. Here it has the vertex on the x-axis. We have, of course, considered more general parabolas in earlier videotapes where we have the vertex someplace other than on a coordinate axis. And these parabolas have other terms as well. But our main purpose of this tape is to distinguish between parabolas and lines and ellipses and so on. Okay, so neither x nor y was squared, a straight line. If one is squared but not both, parabola. Now, what happens if we have them both squared? Let's say, for example, instead of 4x plus y equals 16, let's make it 4x squared plus y squared equals 16. Now, both x and y are squared. In general, when one has an equation of the form ax squared plus by squared equals a constant, okay? Just from the fact that x and y are both squared, we would say that it's either a circle, ellipse, or a hyperbola, or a degenerate form of one of these. Okay, now, how do you tell them apart? Well, you can get the intercepts. These are all, by the way, these are ellipses, hyperbolas, and circles in standard position that have their center at the origin, that are symmetric with respect to the coordinate axes. So one could just find the intercepts without memorizing any rules. If, for example, your intercepts are all located the same distance away from the origin, you would have a circle. If you had say, your x-intercepts quite far apart, your y-intercepts closer together, you would have this ellipse. If you had maybe x-intercepts but no y-intercepts, or y-intercepts and no x-intercepts, you would have a hyperbola. Okay, so actually your intercepts can tell you the whole story. You don't have to remember the basic forms all that much. You just need to know that if x and y are both squared, could be a circle, could be ellipse, could be a hyperbola in standard position. Okay, so really we're talking about finding the intercepts. If you would like some rules, you can say that when these constants all have the same sign and a is not equal to b, then it's going to be an ellipse. When all the constants have the same sign and a equals b, thus forcing the x and y intercepts to be the same, then you have a circle. And when a and b have opposite signs, that's when you get a hyperbola. But as I said, you can just get the intercepts and let that tell you the story. If x is equal to 0, y squared equals 16, y is equal to plus or minus 4. If y is equal to 0, 4x squared equals 16, x squared equals 4, x is equal to plus and minus 2. If you wanted to, you can, of course, as we did in the tape on ellipses, divide all parts of this, both sides of this equation through by 16, giving us x squared over 4 plus y squared over 16 equals 1. And then you have the ellipse written in its more traditional form. Okay, regardless, whether you're going to see that the x-intercepts are 2 and minus 2 because of the square roots of this number, or you get it from over here, and whether you get the y-intercepts from here, 4 and minus 4, or you say that the square roots of the number under y squared in this form, we all do agree that it does have x-intercepts of 2 and minus 2 and y-intercepts of 4 and minus 4, and it looks something like this. Okay, suppose we had x over 4 plus y over 16 equals 1. Okay, and I don't want you to get confused. Don't confuse this form with what we have over here. Here we have x and y both squared, okay, and the coefficients are different, and it's an ellipse. Here, although I'm trying to make it look like it's in this form here we really have just a straight line. Neither x nor y is squared. Okay, so don't be upset if it's in this form or if it's in the form that we had our original straight line in. Of course, in this case, if you were to multiply through by 16, you would get rid of the fractions, and you would get 4x plus y equals 16, which is a straight line that we sketched, the first example that we did on this videotape. So I don't want you to get confused, and just because you see something in this kind of form, you say, well, gee, I remember the ellipse looked like that. If it's x squared over 4 plus y squared over 16 equals 1, now that's an ellipse. X squared over a squared plus y squared over b squared equals 1. But this, okay, although I'm trying to fool you here, neither x nor y is squared, it's just a straight line. So we don't have to bother sketching that, just remember that it is a straight line. We did that earlier. What if we had, instead of 4x squared plus y squared equals 16, 4x squared plus 4y squared equals 16? Okay, sort of like ax squared plus ay squared equals c. In other words, it's still in the form the ax squared plus by squared equals c, but here a is equal to b, and a, b, and c all have the same sign. And this, of course, is just a circle. If you weren't sure, you could get the intercepts. Okay, but this is a circle. You could, of course, divide through by 4 and see that it's x squared plus y squared equals 4. And when x is equal to 0, y is equal to plus or minus 2. If y is equal to 0, x is plus or minus 2. It's a circle with center at the origin and radius 2. If these numbers are going to be the same, then naturally the x and the y intercepts are going to be the same. Here, these coefficients were different, and you had different values for the x and y-intercepts. Here the x-intercepts were 2 and minus 2, but the y-intercepts were 4 and minus 4. Here the x and the y-intercepts have the same values, 2, 2. Okay. Now what about the following? Suppose we had, instead of 4x squared plus y squared equals 16, suppose it was x squared plus 4y squared equals 16. Still, x and y are both squared. Makes it either a circle, ellipse, or hyperbola. And the fact that the signs are all the same and the coefficients of x squared and y squared are not equal, that tells us it's an ellipse. And the intercepts, if x is 0, 4y squared equals 16, y squared is equal to 4, y is equal to 2 and minus 2. And if y is 0, x squared is 16, x is 4, and minus 4. We once again have an ellipse. Now the y-intercepts are 2 and minus 2. The x-intercepts are 4 and minus 4. So by going from 4x squared plus y squared, here we had 4x squared plus y squared equals 16. Here we have x squared plus 4y squared equals 16. We have switched the ellipse. Here it was sort of like a narrow and tall. Here it is wide, okay, and short. And when the coefficients were the same, okay, the x and the y-intercepts were the same, we had the circle. Here it was 4x squared plus y squared equals 16. Here, 4x squared plus 4y squared equals 16. And here we let x squared plus 4y squared equals 16. So you see the circle and the ellipse are very closely related. They have the 4 intercepts in each of these. It's just a matter if the x-intercepts are the same distance apart as the y-intercepts. Okay, then you're going to have the circle. Here you have the x-intercepts farther apart than the y-intercepts. Here you have the x-intercepts closer together than the y-intercepts. And you have the ellipse. Okay, now the last thing that we have to consider is what happens if we change the sign. See, so far all of the signs, A, B, and C, they were all the same sign. What happens if we change the sign? In particular, if A and B have opposite signs. That's when we get our hyperbolas. Let me show you some of them. Instead of 4x squared plus y squared equals 16, let's consider 4x squared minus y squared equals 16. This is in the form, once again, ax squared plus by squared equals c, but a and b have opposite signs. That is the tip-off for the hyperbola. Okay, if you remember how to sketch a hyperbola, whether it's in this form or if you divide through by 16 first, okay, having determined that it is a hyperbola, if you remember, you say if y equals 0, well, 4x squared equals 16, x squared equals 4, x is plus or minus 2, but if x equals 0, well, you get y squared is minus 16, and you get no y-intercepts. When you get x-intercepts but no y-intercepts, or y-intercepts but no x-intercepts like this, then we have a hyperbola. And the trick for sketching such a curve, if, by the way, any of this is going too fast for you, I would refer you back to the individual tapes on each of these curves. We have a videotape on circles, one on parabolas, one on ellipses and hyperbolas. Here's a sort of an overview of all of the tapes, just trying to help you to compare and contrast them. Okay, we look at this curve, 4x squared minus y squared equals 16. And we pretend temporarily that this had been a plus sign in between, in which case we would have had an ellipse. If y is equal to 0, 4x squared equals 16, x squared equals 4, x is 2 and minus 2. If this had been a plus sign and we said x equal to 0, y squared equals 16, y would be 4 and minus 4. Now, if this had been a plus sign, this would be an ellipse, and the ellipse would go through these 4 points. And in fact, we sketched that one earlier today. However, we have a minus sign. It's a hyperbola. These 4 points, the 2 x-intercepts that really are there, and the points on the y-axis that are not intercepts but would have been if this had been a plus, we connect these 4 points. Okay? We draw a rectangle that goes through these 4 points. And then we draw the diagonals of this rectangle, and we extend them beyond the rectangle. And these are going to be guidelines for sketching the hyperbola. Guidelines, these are asymptotes, lines which the hyperbola is going to get very close to but never quite touch. Okay, now, this hyperbola in particular had 2 x-intercepts and no y-intercepts. So we're going to fit the hyperbola in here. It's going to get very close to these lines, but we never cross over them. Same thing here. By the way, some people tend to draw parabolas and hyperbolas very similar to each other. There is a basic difference. The parabola does not have asymptotes. Okay, you cannot find guidelines such that you can fit the parabola in between them. Okay, it's going to continue widening. If you were to, for example, draw y equals x squared, which is a parabola in standard position, vertex at the origin here. It continues off, but it widens as it goes off. So if you were to try to draw in a guideline, eventually it would cross it. Okay, let's say you thought that this was a guideline, but it would continue, it would cross the parabola. There are no asymptotes for the parabola. There are asymptotes for the hyperbola. Okay. Let's try to sketch another one. Instead of 4x squared minus y squared equals 16, what if we had had y squared minus 4x squared equals 16? Well, this would also be a hyperbola. It's still in the form ax squared plus by squared equals a constant where the coefficients a and b, okay, have different signs. Doesn't matter which one is the positive, which one is the negative, as far as determining that it's a hyperbola. In fact, our procedure in sketching it is exactly the same. What we do is temporarily pretend that that was a plus sign, in which case it would be an ellipse, and let's try to find the intercepts. If x was 0, y would be 4 and minus 4. If y is 0, and if this had been a plus sign, then you would get 4x squared equals 16, x squared equals 4, x is 2 and minus 2. So you would draw the rectangle through these 4 points, and of course, it would be the same rectangle that we got over here, going through 2 minus 2 on the x-axis, 4 and minus 4 on the y-axis. You would draw the diagonals of the rectangle in and extend them beyond the rectangle. The only difference would come in here. Over here with the 4x squared minus y squared equals 16, here when we set y equal to 0, they had x-intercepts. But when we set x equal to 0, you could not solve for y. There were no y-intercepts. So we put the hyperbola in left and right. Here, however, when we set x equal to 0, we get y is 4 and minus 4. These are really the intercepts. If you were to set y equal to 0, you could not solve for x. This hyperbola does not have x-intercepts. So therefore, we sketch it in like this. Okay, it's going to be up and down, filling in the other two portions. Okay, here we had 4x squared minus y squared equals 16. Had x-intercepts but no y-intercepts. The rectangles in these pictures are the same. But this one we fill in left and right because it had the x-intercepts but not the y. Here it's the same rectangle, but it has the y-intercepts and not the x-intercepts, so it goes up and down. But the guiding rectangle and the asymptotes were the same in both of these pictures. Okay, so you pretty much know how to recognize lines, parabolas, circles, ellipses, and hyperbolas, at least in this form. Now, sometimes you don't get it exactly in this form. Very often, your equations involve square roots. Okay, what do I mean when I give you something like this? Y equals the square root of 16 minus 4x squared. Are you going to have to memorize all different types of basic forms? Well, the answer is no. Whenever I have an equation involving a square root, I would recommend squaring both sides to try to get a feeling for what kind of curve it was. Then go back and say, well, look, if y is the square root, meaning the positive square root, if you see nothing in front, the positive square root is implied. If y is the positive square root of that, y has got to be greater than or equal to 0. Y can never be negative. So, for example, we sketch the curve and we take the top portion of it, the portion that is above the x-axis, on the x-axis and above the x-axis. If it had been the negative square root, we square both sides, get an idea of what the curve looks like, then take the bottom half of the curve. Okay, let's try this. Just remember that y has to be greater than or equal to 0, since it's a positive square root. Okay, we square both sides. Y squared is 16 minus 4x squared. Or 4x squared plus y squared equals 16. Of course, we sketched this curve earlier. Today, this is an ellipse. We recognize that x and y are both squared, which makes it either an ellipse, hyperbola, or a circle. But here we can see when x is 0, y is 4, and minus 4. Those are the y-intercepts. When y is 0, 4x squared equals 16. X squared equals 4. X is 2 and minus 2. These are the x-intercepts. The whole curve would look like this. This would be the ellipse. Then you go back and say, well, what about this curve that you were asked to sketch? What you've done is square both sides and you sketch that. Well, here y has got to be greater than or equal to 0, so we want only the top half of this ellipse. So then you can go back and say, I'm only going to take this portion. Goes through 1, 2, 3, 0, 4, 2, 0, minus 2, 0, just the top half. But instead of memorizing all sorts of forms with square roots, the trick is to square both sides, get a feeling for what the curve looks like, and then just choose the appropriate portion. In this case, y is greater than or equal to 0, so we take the top half of the ellipse only. If y had been the negative square root, we would take just the bottom half. If the equation had been solved some other way and you had x equals a positive square root, that means x would have to be greater than or equal to 0. We would take the right half. If x were less than or equal to 0, the negative square root, we would take the left half. So we square both sides to figure out what the curve is, and then we take the appropriate portion. Let's try another one. Y is equal to the negative square root of 4x squared minus 16. Okay, y is going to be less than or equal to 0. We square both sides so that we can sketch the curve. Y squared is equal to, now the minus times the minus, that becomes plus the square root of that times the square root of that. Because you're going to square it, you're just going to get 4x squared minus 16. Or, let's see, 4x squared minus y squared equals 16. I add 16 to both sides, and I subtract y squared from both sides. And of course, we have sketched this one earlier today. This was a hyperbola. If y equals 0, x squared is equal to 4, x is 2 and minus 2. If this had been, it has x-intercepts, it has no y-intercepts. If this had been a plus, okay, the y-intercepts would have been 4 and minus 4. We use that to get the rectangle, the diagonals of which are the asymptotes for the hyperbola. And then we say, well, this had x-intercepts, but no y-intercepts. These were the x-intercepts. The hyperbola looks like this. Well, that's the whole hyperbola. Now we want the bottom half, because y is the negative square root of that. So y has to be less than or equal to 0. So what you would draw is only this portion in here. The portion on the x-axis and below. Y has to be less than or equal to 0. So the sketch is given in here in the heavy shading. Okay? The entire hyperbola is given like that, and we want the bottom half. Y is the negative square root, so only the bottom half of that hyperbola. And that brings us to the end of this tape.